Okay, so in this video, we're briefly going to review some concepts we talked about in the last video, and then just do some examples. The next video after this one, we will get into the next part of this unit, which has to do with wave behaviors, and so this is just kind of like an example video. All right, so last class we talked about what a wave is, and we talked about the different types of wave. We talked about mechanical waves, which require a medium, and then we talked about transverse waves versus longitudinal waves. And so just to kind of recap, this is a picture of a transverse wave that you see on the screen right now. And so a transverse wave, basically the particles making up the wave, or the matter making up the wave, moves perpendicular to, that means at a 90-degree angle to the direction of the wave itself. And so most waves in existence are transverse waves. And so that's why when you ask somebody to draw a wave, typically they're going to draw a transverse wave. And just to recap, a transverse wave has some different parts that you need to know. For example, the top of the transverse wave is the crest. The bottom part is called the trough. That middle line, that dotted line, is called the rest position, and then the wavelength is typically measured from one point on the wave horizontally to the next equivalent spot. And so you can measure that from one crest to the next crest, you can measure that from one trough to the next trough, or just picking any point you want on the wave and traveling horizontally until that same point repeats itself. Now, what we didn't talk about in the last video was what about longitudinal waves? And so the reason we didn't do that is because longitudinal waves are way less common than transverse waves. Basically, the only common longitudinal wave is a sound wave. But you can also produce a longitudinal wave on a slinky or a spring like you see here in the picture. And so longitudinal waves don't have crests or troughs. They have something a little bit different. And so in a longitudinal wave, which is also called a compressional wave, it looks something kind of like this. And basically, instead of crests, you have what's called compressions, and that's basically where parts of the wave kind of, well, compress. They kind of come together, as you can see here in this picture. Instead of troughs, you have something called a rarefaction, okay, which is basically where the wave spreads out. And you can see that here in the picture as well. And so rather than crests and troughs, you have um, compressions and rarefactions in longitudinal waves. And so those are two parts of the longitudinal wave that you need to know about. It's just not commonly talked about because most waves are transverse waves, so usually the focus is there. You still have wavelength in a longitudinal wave, by the way. The way you measure it is basically the same. You basically pick one point on the wave and you keep going until you get to the next equivalent part of the wave. And so you could go from one compression to another compression, which is what you see here in this picture. Make it a little bit bigger. Or you can go from one rarefaction to the next rarefaction. Either way, that's still one wavelength. Okay, and so now, just to wrap up this video, we're going to do three quick examples concerning what we talked about waves in the last video. And so let's take a look at example 3. And so example 3 is basically just asking you to label the different parts of what looks to be a transverse wave. All right, and so question 6 says this letter represents the wavelength. All right, and so we want to pick the letter A, B, C, D, E, F, G, and so on that corresponds to the wavelength. And so looking at the picture, which letter do you think represents the wavelength? Okay, well that is going to be letter A. Okay, from one crest to the next crest, that is the wavelength. Okay, E actually doesn't represent anything, and C doesn't represent anything. And so the wavelength is A. And remember, by the way, we use lambda, that upside down looking Y, for the symbol for wavelength. All right. The amplitude, if I ask you what letter represents the amplitude, that is from the rest position, which is in the middle, to either the crest or the trough. Either one of those works. And so here you might think, maybe B is the amplitude. But B, if you look at B over here, B goes between the crest and down here to the trough of the wave, which is not the amplitude. The amplitude is only half of that distance. And so actually, I'm looking at D would represent the amplitude right here from the rest position in the middle, that middle line, down either to the trough or up to the crest. All right, G represents the trough, and then it looks like point E right here represents the crest. All right, so you should definitely be able to label different parts of a transverse wave. Okay, so let's take a look at another example. So example 4 says wave A and wave B have the characteristics shown in the table. And we can see wave A, wave B, we can see the frequency, wavelength, and amplitude for all of those. And it says both waves are sent through the same spring. Which wave has the greatest energy? Okay, so look at the picture there and try to answer that on your own. Okay, so in order to answer this question, you need to know which of these properties, frequency, wavelength, and amplitude, which of those has to do with the energy stored in a wave. And we talked about this in the notes in the last video, but the answer to that question is amplitude. Amplitude corresponds to energy in a wave, and so whichever one has the greatest amplitude is also going to have the greatest energy. And we can see, looking at the amplitude, the one with the biggest amplitude is wave A, and so that is the answer. Okay, so frequency and wavelength both help describe the wave, but they don't have to do with the energy in the wave. And so if you imagine going to the beach and you see like a water wave, the amplitude would basically be like how high is the wave? And the higher the wave is, the more energy that wave has. And so that's why you'd rather get hit by a small wave than a really, really tall wave that could envelop you, which would be bad. Okay, so more amplitude means more energy. All right, so that is example 4. And let's just take a look at one more quick example. All right, this is example 5. And so here we're given a picture, and we're asked some questions about the picture. So example 5 says, for the wave shown to the right, answer the following. And it says there should be 5 answers. What type of wave is this? All right, so first of all, this is a transverse wave. We've already talked about how it's the most common type of wave we can tell just from the shape. Okay, now the second question says, what is the amplitude of this wave? So try to find what the amplitude of this wave is. Okay, so remember the amplitude, you start by measuring at the rest position, so anywhere along this line, and either going up to the crest or down to the trough. And so from here to the crest, which is here, that is 1 millimeter. We know it's 1 because there's a 1 right there. So I would say that the amplitude is 1 millimeter. Now the wave speed, well, the wave speed is in the picture. It's right there. It says V equals 200 meters per second. So that would be 200 meters per second. I don't even have space. V equals 200 meters per second. That's the wave speed. So that's the answer to the third question. What about the wavelength? Okay, so again, pause it here and try to find the wavelength just from the graph. Try to find the wavelength on your own. Okay, so remember to find wavelength, what you can do is you can pick one point on the wave. It doesn't matter which point. I'm just randomly going to pick the trough. And you measure horizontally until you get back to that same equivalent point. And the length of that horizontal line is the wavelength. So between 1 and 3, that corresponds to a wavelength of 2 meters. It says meters right here, so the unit is meters. All right, and if I had gone from one crest to the next crest, that would also be 2 meters. So I would write down lambda equals 2 meters. That's the wavelength. And then finally, the last question says calculate the frequency of this wave in hertz. And so for this question, you have to use the wave equation. Just to refresh your memory, V equals lambda times F. So try to use that equation and enter example 5, the last part of example 5, on your own. Okay, so this is a simple substitution. V is 200. That's equal to lambda, which is 2, times the frequency, which is F. We want F by itself, and it's being multiplied by 2. So I need to divide both sides by 2. And I get F equals 100 hertz. Remember, hertz is Hc. And that is it for example 5. Okay, so remember, you do have some calculations in this unit, but all the math you have to do for this unit is really, really simple. Okay, but you can see from this question that most of these questions, it's not doing calculations, you just have to know what these different things are. Okay, you have to know what type of wave this is, you have to know how to find the amplitude, how to find the wavelength, etc. Okay, and so make sure you're taking good notes as we go through this unit because there's a lot of things that you can't just rely on equations to get the correct answer, you just have to know things. All right, so we're going to go ahead and stop it there. If you've not already done so, you need to make sure that you do your wave properties CER that is posted in Canvas. And in the next video, we will talk more about wave behaviors. As always, please let me know if you have any questions, and I'll see you guys in the next video.